Uh, so, this one's kind of like what people would call maybe a replicator, right? I've already talked a little bit about it. I have a few different designs in my audio blog too, but this one's a pretty basic one, all right? That's easily done cheaply, efficiently, and effectively, such that you'd be able to get it actually going soon. And you don't need to manhandle physics to make it happen with really high amounts of energy and control, which is good usually. Most people don't have that. So, this is a pretty simplistic. There is a substrate, there is a chemical, either liquid or gas, that's inside of whatever the given box is that you have of your 3D printer. Your 3D printer is going to extrude either a physical, meaning, or not physical, either a solid, gaseous, or liquid, or even plasma if you can get it, of the either molecule or compound or even atom in this instance. Now, when I say that this is supposed to be used for regular people, I mean that. Not like for industrial applications, I mean for regular, average, everyday people. But what it means is you need to know chemistry. So, chemistry in general is really cool. It's kind of what builds, like, basically everything, okay? So, it's pretty nice to know about it. But what I'll tell you is that a lot of people in chemistry are really awesome in how much they also know about physics. Okay, so they know that it's a different types of bonds will react differently with different types of wavelengths of light, and it's not just the molecule itself. Not to mention the electrostatic forces that are there and applied in given areas, and electromagnetic forces that are applied or both in a combo. And if you use both light, electrostatic, and electromagnetic, which is pretty much all chemicals really are kind of like going to be ever affected by, then you understand that a lot of them can be precipitated out and then welded. Cleaved is essentially what they go with, but it's like cleaved and then welded by having the right forces applied in the right areas over time to essentially force. And this is a nice little one. If you use the right sound wave profile in a given area inside of that container, then you end up having a really precise controlled environment in which you can accurately reproduce very specific chemical reaction uh, types that will allow for you to deposit onto a substrate, which can be either positively or negatively ground and continuously helped to effectively make whatever it is that you're trying to make. And so all of my designs that go along with atomic and molecular sized things are just that. It's a bunch of chemical. It's a chemical vat. It's literally that, and then the sides are a phasor array of different types of diaphragms and light producing if you need it. Uh, you know, diodes or something similar. Then the printer head is both the substrate below, but also a substrate above. And so instead of thinking about it like one little tiny nozzle right there, it turns into a very specifically and very tightly controlled operation in which it forcefully makes one specific thing after another happen in one area and moves along as it slowly opens and builds up whatever's inside. Just pretty much the same way that we do. This sounds crass, but a 3D printer in that type, while not the same way, does sort of do that with organic deposition. So, an organic molecule, which is the embryo, will slowly get deposited the right nutrients in the womb until it grows a baby. And so it's got programming language in its DNA to slowly but surely continuously make the next thing happen to the next thing to the next thing, but it always needs the right materials to do it. So they work in conjunction, and it's in a tightly controlled place in space that allows for it to be done. Effectively the same thing. Not really, because, well, yes, you can print out organic things, and you can do this for what it's worth. It's really something that I made mostly for, organs or very specific types of metal 3D printing, because there are liquid chemical, like electroplating types of saturation compounds that work very well to be cleaved off with the right light, electrostatic, electromagnetic forces, and pressure forces that can be tightly controlled. Which means it can be with very little amounts of energy and the right kind of like new filament, essentially, chemical compounds. It then makes it such that you can make very specific metal structures, right, that are without porosity, because you can dump them down on an atomic to molecular size, depending on how tightly controlled you want that to be. So that's what I talk about when it comes down to that. It's not been done before, though. Like every part of it has been, just as an FYI, but that's the reason why I talk about it, because it's like, well, we already know about chemical deposition and using electricity in chemistry. Like, we actually do know about all of that. In fact, that's what we use specifically to refine the vast majority of our aluminum, gold, iron, and a lot of other things, either from recycling or from mining operations that don't have significant profit, because there isn't large amounts within inside of what it is they're mining. So they make more profit because they don't need a lot of electricity, they don't need a lot of chemicals to be able to ultimately make it. And it's very, very consistent at having high purity. Now, the optical tweezer thing, which is what you'd probably think it is, but it's not really. Okay, so optical tweezers is depositing something with the laser being forceful on it. This isn't what this would be. Using light to actually cleave a given compound bond is what that really is. And then because it happens to interact with light wavelengths of a certain type in its separated state, then that means you can separate them and allow for a charge difference and a electromagnetic and electrostatic difference to allow for a precise adherence, kind of like the standard chemical reaction bond types. You know what I mean? Like, instead of making a bunch of ionics, though, it's supposed to bind this way, because like that compound is a compound it reacts with. And so now it makes the correct either proper ionic that you're looking for, or covalent, or double bonds, or whatever else it is you're wanting to have. Now, people that are into 3D printing don't have a lot of knowledge on that. People that are often in a lot of chemical reaction style of building, or doing or any of that for other compounds, well, they don't often know a lot about all of those different types of wavelengths of light and how to use them best, right? Then people that are very significant in electromagnetic and electrostatic, electrical engineering, well, sure, they know like that happens, but they don't do that. They just make electricity go to the right places, or you know, have internet work, or stuff like that. Because often that's kind of what Wi-Fi is. It's an electromagnetic field produced by a given type of electrical current run through it with the right type of material to make it happen, right? And same thing with organic chemistry. Like organic chemistry is, oh my god, it's wizardry to some, and then when you actually talk to like really significant professors or whatever, they end up going, oh yeah, so they're like little tiny machines, is what you're saying then? Yeah, pretty much, and they work off of these given laws and rules. Like you get really deep into the woods, you start realizing a lot of people start thinking very similarly. It's like there's nothing that really stops that from being a thing. If we could understand how that works, if we could more or less like kind of control it, then we could use that to our advantage, right? And so, what stops us? The answer, unfortunately, a lot of people from a lot of different walks of life and field of studies don't talk very much about how to make that a thing. Like the knowledge they need, the knowledge they have, the knowledge of how to mechanically and all the rest chemically and electromechanically and more put it together with how piece by piece they would all have to work. So, like all the pieces are already there. They already exist in every one of the fields of study. And in fact, it can be very much something that is in your house, making practically anything. It could even, yes, make you a really good espresso or something if you really wanted it to. That'd be a little different, in terms of really what you're going to probably do. But like it's organic molecules, caffeine can be made, like vitamins, minerals, nutrients, flavonoids, different chemical compounds to produce the different type of flavors, all doable. Now, it could take a little bit of time, sure, but if you ever want me to relate it to like you making an espresso versus you making an espresso this way with standard beans, grind all that, it took 5+ years to make those beans, right? And then you had to roast them, you had to ship them, you had to grind them, you had to do all this stuff. And the machine to do the extraction work and all that had to be made and had to be mined, had to be all of this. And so like none of that time's really added in to the idea of how long it took for you to make that espresso. But so it takes me like what, an hour? Well, I get up, I brush my teeth, take a shower, I get ready for work, I have my espresso. Right? And I can do that. There's nothing saying I couldn't do that. It'd be exactingly precise the same way every time, which would be great. Especially since I basically make what is effectively a decomposing cup in which I can have it, which is great. But at the same time, it's like, that's nice, but my thoughts tend to turn into other things, like battery generators, right? This is a synthetic organic blend of material that allows for when air passes through, like with leaves and some sunlight and some heat. You know what I get? A bioreactor. I get electricity. It stores its own amount of electricity because that's what it's trying to do. But that's what my battery generator that I added a whole bunch of people on is essentially doing. And the way I went about trying to make it happen, which was plasma deposition at the time, still works. It's just a lot more involved and has a lot more plasma. So I don't think people really wanted that. But industrially speaking, totally doable and pretty fast, right? So there's that. But what I talk about for printing almost anything, it can be very quickly dumbed down into, well, as long as the printer head can ultimately go through, instead of making a plate on one side and a plate on the other, which was going to be the best option. If you're going to make anything, it'd be the better way to do it. You can cheap out and get a simple printer head that has a hemispherical or near hemispherical dome around a given type of printer head that allows for a very tightly controlled, resonance of any given type of compound. It allows for you to interact with whatever substrate, and liquid, gas that you're in, you're putting it through to ultimately make whatever it is you're trying to make. Instead of having to, oh man, I'm making huge claims. It's like, actually, they already do this. That's not my fault that you didn't know. And even if you don't know about that, now you do, and it's not hard to Google this. They're not industrial secrets, okay? Nothing like that is going on. These are chemistry types of ways of doing things, okay? We already have a version of that when it comes down to a liquid that when we shine light on it, it turns into a plastic. And so we already have a version of this. And so it's essentially a different type of doing it. But now we're going to add in some, heated extruded material in the right area alongside of sound waves, resonant sound waves. Now, if you do that the right way, you can have things collapse in a given specific area that can help you with bending your light and being more precise and allowing for very specific materials to be adhered in very, very small areas to have no porosity. Why would you have porosity when you're down to a molecular level? As far as I'm aware, that's basically everything. So if we want to go with human beings have porosity levels, I guess we're on that level. To shade some people out there, because you might want to not say things like that. You know what I mean? The reason why I was thinking about it is because I also wanted to make a metal 3D printer. For what it was worth, my main big goal was making a metal 3D printer. And I was like, well, we already have versions of it, which are essentially the equivalent of I have this attached to my welder. That's right, it's a welder. So I know, right? Oh, that's so terrible. And it's like, well, it's a tack weld, 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 tack weld. And it's like, well, if I have it as this small of a rod, then I can ultimately speaking make it this precise. Which it's like, that's kind of lame, but it's a way to do it, right? And so I was like, all right, I need to make this better for myself because I hate everything about what I just said. I legitimately do. So I turned it into well, there's small powders of metal that you can get. Right, and it's like, all right, so if I make the electrostatic, powder coating, that's no, that's still lame. So you know what I'm going to do? It's like, I'm going to electrically heat up the powder. It's going to have to be still in a vacuum, all right? But then I get lasers, all right? The standard lasers that you can usually buy, they're a little more powerful than they say they are. But, that's neither here nor there. I mean, I don't have to worry about that. They sell it, and I'm allowed to get it, so I don't see what the problem is. Anyways, then I got into high-frequency pulses. So what I figured out, mostly thanks to the attosecond individuals, if you don't know about that, and I've already known about you take a longer wavelength, a shorter wavelength, and a medium wavelength, and you pulse them, and you align them ultimately to arrive at the same spot, to constructively interfere to create a much, much higher wattage pulse than normal in a much smaller time frame and a much smaller distance, which is great. I don't need that distance. I don't need that time frame. I don't need anything like that. I never need an attosecond at all. So you know what I ended up going? I was like, well, what about if it was just within a few milliseconds? You know what I mean? Like, that's all I really need, right? Like, that's all. So I was like, all right, so if I do a few milliseconds, then it's like, all right, so this is a small little computer. It's like, if I parallelize, how many cores does it have? It says it has 16 cores now, right? And that's 32 threads. That's not bad. That's really not bad. If I want to parallel a given signal output from its pin set, which it has to, in sequential order, then get sent to something, right? So it's like, I know what that sequential order is, right? And like, that's the, the order I'm looking to ultimately make have happen. So like, that's some programming, sure, okay, fine. But you know what? That's for this wavelength. All right, so it's like 32 divided by 3. What do I got? I was like, well, it's really 10. Okay, because I need at least those other two to probably properly plan it and then make sure it all arrives at the right time. So I was like, all right, fine. So it's like this pulse second, this pulse second, this pulse second, this wavelength, this wavelength, this wavelength, this focus, this focus, this focus, right? And it's like, well, then I need to get it through an amplificatory setup. So it's like, turns out some of those higher end amplifiers have a low noise floor for our headphones are actually the better way to go about that, because they actually output a proper sine wave for laser lights, the little diodes that they use. But that means I have to buy a specific type of diode, and then it's like, right, well, how expensive are those optics? I mean that, like, how expensive are they? It's like, they're fairly expensive, right? And I don't like that. So it turned into that guy. You know, you're going to use the asterisk and the whole, like, that guy. Like, why don't you just spend a whole bunch of money on this? Like, because I don't have that money. Like, most of the YouTubers don't have that money. Can you go away? You know what I mean? Like, I am certainly not one of them. I'm trying to get on Social Security income. So, you know, that's clearly not going to happen with me. So it's like, well, water can theoretically do it. No, I'm not going to use water. It's going to be disruptive. I don't want to use water. So I was like, how in the hell do I carve lenses that are far cheaper into something that makes the accuracy and precision I want for the given wavelengths and, you know, the pulses that I'm having happen at the times I'm looking for them to ultimately work together to be the right precise and accuracy types. So I looked at old cameras. That's right, I looked at old cameras. Old. Cheap as fuck. Turns out they have pretty decent wavelength lights, you know, or for lens, right? Like throughout the spectrum that they'll interact with. And I was like, all right, so if I do that, it's like, how do I carve these down? It's like, I don't have like diamond, any of this stuff. So it's like, that's not happening. That's not gonna, no, I'm not doing that. So turned into lasers can 100% milk those fuckers if I do it the right way. You know, like you can milk through metal. You can milk through glass too, if you know what you're doing with the right wavelengths. So it's like, well, if I shine it on one way and I shine it on the other way and have them constructively and destructively interfere, technically speaking, is kind of what that is, with a perpendicular angle light that I hold in the right direction, it will slowly but surely get a very precise realignment and angling of the lens. Now, it takes a while, but it will do it. You know what I mean? Like, it'll do it. So it's like, all right, so that's some threads. Right? I want like pretty high thread count to another pretty high thread count to another pretty high thread count. So that way I have really, really small increments of movement for these tiny little things I'm going to work on. And so I was like, all right, well, I can get the laser to do it. In fact, I can even do basically a rough clean room. So it's going to be in a vacuum. I'm going to have to do a whole bunch of cleaning ahead of time, let everything settle, then I have to electrostatically try and purge, and then I have to do a little electrostatic, rinse force, like, get out of there. And then it's like, get the chamber, and then it's like, all right, this is pretty clean, then I do another version of the same thing, of the cleaning. I put it in there, and slowly, and this is where it turned into. So, aluminum that's extruded, and some gloves, and some plastic, and then you cut hole in plastic, and then you put gloves through hole, and then you tape holes. And guess what? It works somehow. Pretty good for the most part. Yeah, for the most part. It's not perfect, but for the most part, it's working. You just got to seal it. It's, at the bottom, that's like rubber seal stuff, effectively. But it's like now it's like small little increments, and it's like behold your horses before you think any bit further. It's like that's good setup, not yet done. In order to really do that to those lenses, you need to know what the hell it is you're doing, where it is you're doing, and you need to have a specific type of parameter that you're going to be able to know that you're hitting. So you need to be able to know after you've done it that you've done it right. So you have to build a sensor to detect the amount of off. So the very thing that you're using right now to try and make it this accurate is not what you're going to actually use. First, you're going to use a separate sensor on the other side that you're going to use those two almost close to going to the same area focal lengths with one that travels through. That gets a type of interference pathway and type that you on the other side with that sensor can now use, kind of like a camera lens sensor, to know the level of off and precise you are on those lens surface areas. Inside is a different story. We'll get to inside first, because it's like that pretty much does everything, except that's a bunch of programming that you have to do. Like what I just told you for surface is pretty much everything that you're going to have to do. Almost. You're going to need to program for through the lens first, which effectively means on one side you shine it through, the other side you shine it through. You try your best to have it as close in terms of its relative position of distance and preciseness in terms of the amount of light that's going to go through, the amount of... So this is why vacuums became a big thing, but also not just distance, you need heat of the lens, you need heat of that sensor, and you're going to need any noise as best you can accounted for, and any vibrations as best you can for that given surface area accounted for. So, I know, shocker, turns out doing this with high levels of precision, annoying. Who would have thought? You pay a lot of money for that. Who would have thought? So, you can get really decently precise lenses. They're just not the right focal length, and they're certainly not the right type that you're looking for, more often than not. And so you have to look at really small ones, you have to do a whole bunch of stuff, and it kind of sucks as a result, right? But it's like, if you want convenience, you'll just pay it, because it's worth it. But if you don't, and you're willing to do this, then it's like, as you shine it through one way and the other, you'll do that several times, you'll get a aggregate of average, and then you usually, this is how you really are supposed to do it, have a one that you bought first. So that way it's like, this is a known, it works well, and it's good. That means you calibrated your sensor ahead of time, and you can reference that data off of something. We're not doing that. You're not buying this. You're going to have to do something else. This one turns into, all right, so you have this data. This is what these values are now. If you did it as best you can with the given, pretty much as similar as you could get that day of when you did those experiments and data collection, sensing days, experiments, whatever, then it's like, the next time when you decide to do one, I'm being very firm with this, one singular trying to do anything to it, that lens, one, you'll then redo it again, and then you will now understand if anything changed. If it did, then you know about that much from these given results. Maybe. Okay, then the next one, then the next one. If nothing happened, then you know, at the very least, if there was something, it's not such that you can pick up that level of accuracy. Now, that might be fine, because you're not looking for atomic or super, super small molecular sizes. Or something completely fucked up happened and you have no ability to know. My guess turns into, did you remember to move the lasers back into position where they're going to focus on each other and can destructively interfere while you shine a perpendicular one across it, so that way like you get like a good, very strong force, so the destructive interference to ultimately try and start cleaving and melting off some of those other bits that are in that area, right? So if you didn't do that, then that might be something that you need to do. So you do that over and over and over, and you try and get it as even for your data collection and your sensors to be on one side and the other. All right, that's the outside taken care of. Shocker, there's an inside. That's right. You can make internal lens structures, which you're going to need. I know. You're going to have to just like, unfortunately, yeah, sort of put up with it, you know? Because it's like there's diagonal, there's circular, like Lorentz, there's vertical, perpendicular, lens structures, all that you have to put in on the inside. Instead of it just being, it curves because of, glass, quartz, whatever it is shaped like this, right? If you want to get the most out of these little things, you can't do that. You're going to be treating one of these little lenses with multiple other lasers, which means you're going to need like maybe 2, 3, 4, whatever it is, and then all of those goes to the one big one. And so like all those little ones to the main big one all have to be precisely angled, timed, and wavelengths for the given light that you're using. And then all of those have to be added onto not just the surface, but the internal of the big one, so it all comes out exactingly the right way at the right time in the right place. And so when you think you can't melt an inside internal of the lens, you can a little bit. Now, we're not really melting it technicality wise, but what we are doing is we're shifting where it is, where it ends up, and what it's going to ultimately do for light. So the structure is going to change. It's going to be crystalline, but it then has a little bit denser here, or a little bit less dense there, a little bit more curvature there, a little bit less. And so that's Lorentz styles of lenses inside of a standard, usually they're just, oval, lens. And so as a result of doing a lot of those, you get more curvature. But you can't just do more curvature, like, you know what I mean? So this is where it's like you have to be able to do all of this the right way. It sucks. Yes, I get that. Right? But that means that wavelength can constructively interfere with itself and have destructive interference to any and all other pathways other than the focal length and the type of wavelength that you're looking for, as a bunch of micro lens to the main lens. And when you're pulsing multiples at one smaller little one, and you have to angle them such that you hope that you collect as much as you can that will hit the lens, and then from this side it's angling in with from this side angling in, from that side angling in, and all the rest of them, that you get the right pulse from multiples all together arriving at exactingly the right one of the wavelength and wattage, right? So it's like all of that then is what you got to do. I know. It's like, all right, so you shine light one way, you shine light the other way, right? Yeah, no. Kind of. Right? You're going to shine light on basically all sides, top, bottom, one side through the lens, the other side through the lens, and then diagonally, or perpendicularly. So that also dramatically changes like what you're going to see for curvature, luminosity areas, and wavelength change. Okay, so like all of that dramatically changes a lot. Now, you can only really accomplish it with 3 types of wavelengths that will do this. So instead of me telling you what those are, I'll tell you it heavily depends on what your material is, what your ultimately power wattage is, and what your pulse rate is. So if it's in a vacuum, which we're saying it's in a vacuum, that's great. Keep it there, because that dramatically reduces the amount of variables you have to account for. And if you're going to shine any amount of light through it, try not to also electrostatically discharge into it. You'd be surprised how many times people have tried to do this with electricity and it has not worked the way that they had wanted it to. This is physicists, people that have done multiple different types of theses. Like they thought that they could do a type of electrostatic, like current flow through a given type of material along with wavelength of light to alter old lenses to get a type of metamaterial micro and nanostructure lens over a larger lens. I go, it's because you're trying to congeal, like having a Z-pinch current to a lens that will do it with just light, and you don't need that level of power. Now, other people will go, why not just get it really smooth on the outside, right? Isn't that what that is? And saying, no, because you can't have multiple lasers exist in the same place. Now, you can have light exist in the same place, sure, but not lasers. The emitting diodes can't do that, so you're going to need to angle it, which means you need to turn one into multiples to have all 3 of those properly align at the right time, right? So if you have, let's say, a bank of 3 and you wanted to do 9 total, right? And then you have 9 of those little ones that go into a big one. Now you're losing light along the way. We understand that. But what you gain is more watts, more concentration in focal length for those 9 that go into one main one that then all constructively interfere at the right time, at the right focal length, right? Then you need to do 2 of those to 3 of those, which means 18 to 27 of these damn things. Exactly. All just so this static powder that I heat up and then briefly with a electromagnetic, induction current, as I pass it over, I'm going to use essentially like that as a spark gap, effectively. I'm going to turn it with a lot of current and some electromagnetics into something that's a plasma, right? And it's like, right, now there's a ground here. And it's like, now I'm going to grab it and I'm going to make it go into that spot. And then I'm going to shine these laser lights essentially to focus a lot of that given, stream effectively of plasma into an exactingly precise, aligned atomic level to molecular level deposition. It's not really. I mean, if you can get it really close like that, you could. It really depends. My whole thing is you can. You could do it. It would just be a lot of you basically using this very laser setup that you started with to then make another lens that you would deposit onto that. You know what I mean? Like you'd get like a bunch of silicon dioxide, or different quartz and so on, and then you'd slowly deposit a new lens onto like really precise levels of accuracy, and then you'd use that next one, and then the next one, and the next one, and the next one, and the next one, and then you'd build up until you get like super high precise levels of accuracy. Now, the benefit of this is I only necessarily need up to 27 of these going off. Because they're banks of 3, it really just means I need a lot less energy for the amplification that I'm putting through, which is great. And all of that means it can run off of a standard 240 volt or 120, right? Those two things can easily run this. But hold your horses. I was like, I don't really need that level of precision. So it turns into, how about like a millimeter? You know what I mean? Like one single millimeter precision. No porosity. And it's like, and that's what the laser light does. See, as I turn it into a plasma briefly, and then it fires itself kind of like a railgun, because it's like, this is electromagnetic and it's static, and then like this over here, it wants to be over here. Like a railgun has two electromagnetic fields, and it creates a certain, all that. Anyways, point is, the laser light then can shine on it, and it pulses, and so it will quickly dissipate heat. But also it means the next one that's next to it then has that heat dissipated into, and makes a very good weld that's very, very small. And it does it very, very quickly. That's the reason why I did it. It's like, well, I can deposit it on very quickly, but then it's not very strong. It has porosity. I don't want to heat it up. I don't want any of this. And now it's in a vacuum anyways. Bzzz. Just really ramp up those pulse rates and really make it so it's very, very strong. But the best part is I can still shove a little bit of electromagnetic and electrostatic in that. And so I can align certain, like, let's say it was steel, particles up that make it now act like it's been hardened and tempered. And so from no porosity, I even have the ability to harden and temper or align various particles like that, right? That's what it was mainly for, as I wanted to make a engine block very quickly and cheaply off of powdered bits. Like it's cheap to buy powdered steel, right? It's fairly cheap comparatively to like many other things. So I was like, well, aluminum's also pretty cheap too, And it's like, well, I can also do this with aluminum. In fact, there's nothing that states I can't do this with like practically any metal. And so it turned into, I can make composites, metal where I want, that's steel, and aluminum where I want it, that's not going to need it, but it's still strong enough. And so a lot of that is what I used it for, specifically to no longer have the constraints of poured casting or pressurized casting, or needing molds to stamp certain parts into various specific types of designs, but still get all the strength and robustness as if I had done those things. Now, it takes a long time to make these things, right? We're talking a couple of days to make like a full 2.4 liter engine. And it's a big boy, kind of style. And I need like all of the metal that it's going to need to do that, sure. But 2 days is not that much to make an engine block that's 2.4 liters, right? And that's the main reason why I wanted to do it. It's like, well, I just need a printer head. and then laser light, and then a little bit of electricity for effectively electrically resistive heating, but it's not going to be hot enough to actually melt it, but it comes out pretty hot initially, and then I'm going to make it way hotter at the tip, and then I deposit it much faster, and then force it to be very specific with what it is I need it to be. So it's like I can hit it from the sides to keep that laser light there and keep it hot, along with the electromagnetic induction heating and the, creating a spark gap, which forces more current. So it's a current thing. So I force current through it, but it's like that yanks it out because it has an attractive force, right? It also heats it up during that. And then I can fire in lasers a little bit around that. It takes it, moves it down out of the attractive area, and then the electromagnetic has turned off. It's now only got the other one at the substrate. It's going to be attracted to that, and then I can fire in lasers to basically go stay and be hot and be right there. Be exactingly this. You know what I mean? And so it's like if I aim it a little bit like this or aim it a little bit like that, and these are little pulses that do that. So like the right little wavelengths. So 3 wavelengths is all you get. But if you pulse them the right way, a little bit sooner this way, a little bit sooner that way, and you pulse them the right number of times, it turns into a inertial confinement optical tweezer on its way down until it gets to the substrate, heats it up and aligns it, and it makes it deposit itself exactly the way you want it to. Now, the best part is you can make this in your garage. And even better, it's cheap as fuck. Even greater, you don't actually technically need to do those little internal micro at all. You can really just get 3 smaller ones and then aim them at a bigger one that's meant to take all of those, like a Lorentz, lens into one single one. I just wanted to talk about that because it's like, but what if you wanted to make even better ones? What if you didn't want just 1 millimeter? What in fact you wanted less than 0.01 of a millimeter? Because what I talked about for doing that is 0.01 of a millimeter of precision. If you wanted 1 millimeter of precision, you could do that. You could start off that way with 3 of those. You're going to need slightly brighter diodes, and that really just turns into, well, I can buy those. There's nothing saying I can't buy those, and I can make my own lasers. Because again, that's this and that. And I can make 100 watts. In fact, I can make several 5 of those. Like 3 5 watts. I got 3 5 watts around here. I get 15 watts. I mean, it's not going to be, and by the time it gets there, it's probably like 10. So how many do I really need? How many, actually, what's the real loss rate of and now you see where I go in terms of like, so you're telling me that you want to do this. Because here's a little shocker for the little nozzle, the 3D print tip. If you place those lenses on either side of the spark gap area, and you make sure to properly, not have them melt, right? Right, you only need a little spark gap right there. You can make a spark plug, okay? Like everybody knows how to make a spark plug. It's electrode and ground, right? That's all it is, right? Right, but that means with a little bit of care and attention, with that given light that's emitted from that spark, with the right little mirror, and then the right pulsing of laser light to constructively interfere with that, and to the point where it becomes something that interacts with whatever material you got. That increases precision, not just from the sides, as I said, up to 3, 4, whatever, right? It's like, for me, it's like, well, yeah, I'll use 3 around that, but then right next to where that nozzle is, I'm going to have 2 there. And if I have a mirror in between all of that, because every time it pulses, it's going to create light. And we don't want that light to go anywhere other than where we want it to go, which is on that part in that precise little moment. And that's a reflectivity index, right? And so the substrate can be reflective to this kind of degree. And then you only need to know about this level of distance, right? then it becomes different as you continuously build up the part. Okay, so that will change its wavelength propagation. What I'll tell you is, if you know how to sense that, then you don't have to worry about it. Most likely you aren't going to be able to do that. So I turn it into, as long as within a specific area you're not having to worry about for those one moments of times that you have enough precision to make sure you have control over it. You keep heat, you keep its alignment, you keep where it's going to like adhere to going, then you don't need to worry about it. It'll still deposit as necessary where you want it. And you don't need to fire it super quickly. It doesn't need to be 50,000 times a second like, some of these Intel or other TSMC or whatever is doing. No offense. I'm not doing any of that. I don't need to. Right? But what I do want is for it to stick where it's at. I don't need it to be as hot anymore. I don't really need it to do anything except for on the substrate have the correct electrons there for it in its state of matter as being doesn't have any to now having some. And then with a little bit of light, that means it quickly dissipates its heat and it changes how it ultimately creates more light. Right? So a good way to put that is electron movement in its given orbit is going to be annoying to deal with. It can either create IR, it can create ultraviolet, or it can create a multitude of different signatures that you're not really looking for. So with the right pulse on it, as it will confine it, but also align it, it also means it can quickly dissipate a lot of that heat, but also make that light no longer be something you have to worry about, which is great. These are expected values that you can find quickly online, which is great. It's like, what happens when it's around this heat? What light gets put out for this given, let's say it's steel or iron? Yeah. That's a good question. I can probably find that. That's a mass spectrometer. Oh, no. Next thing you know, it's like, well, that basically is destructive interference, right? Right. All I'm looking for is preciseness. And in fact, you can get away with 0.1 of a millimeter with just the extra 2 next to the nozzle. You don't need to reflect anything. Like, that's more than good enough for the vast majority of people. But if you're talking about, I need to print within, like, let's say it was 5 millimeters, you can still do 5 millimeters. It's just a larger piece, right? And, like, now you don't have porosity. That's what the light helps with. It removes porosity. Like, it typically vibrates it and moves it really close to itself to the point where it'll just dissipate and be welded and fused together such that there isn't space, there is no porosity. For a given powder, you get a solid piece. Now, heat has to go somewhere, and so of course, comes out as just usually light because it's small little spots. But over time, it's going to get hotter. And so, like, the rest of the piece will get slowly hotter, right? The way other people get around that is there's more than enough powder around, right? Okay. I get around it by going with some argon or nitrogen or something. I'll suck it out again for a little while. And that's all I do. Now, granted, it's not really me doing that. Just as an FYI, it's just like a little tube that's there, and this is the vacuum tube area, and it's like, all right, so like it's not on. It's not going to take any vacuum, going. So and it's like this one is the nitrogen or argon, whatever you want to use, and it just pushes it in there, and then it goes and gets rid of it at a steady rate. It slowly cools it off. It goes, yep, this is the accurate temperature I'm looking for it to start at. Then it pulls the vacuum and it goes, all right, time to go again. But be warned, for what it's worth, please don't. I hate them when they do this. He's like, no, it needs to be at 72 degrees Fahrenheit. Iron's fine. Like being up to like almost 500 fucking C. Like, like for what it's worth. I'm just, just saying. Okay. Like you want really cold, constant. Okay, I don't know, man. Doesn't seem like that's reasonable to me. But okay, whatever. You can go over here. That'll cool off slowly. And you can print this part over here while you're printing that. I mean, they're eventually going to join up. You don't have to just from here and then move over. You can start a little bit over here, do a little bit over here, do a little bit over there, a little bit over there, and then slowly get together. But you'd be surprised how many people are like, it needs to be cold at all times. And I'm like, okay. Okay, I see what you're saying. Um, sure. I'm not trying to be mean. I'm really not. But have you considered the fact that, like, it doesn't, maybe? What if it does for the application? Okay. Okay. Well, if it does, then you're gonna have to wait a lot longer for a 2.4 liter engine than a couple of days. You know what I mean? That's much more of the probably a week would do it. And if you want to have to cool it down that often, especially when it's like I can start here, start over there, and then it's like that'll usually get me my base foundations. By that point, most of it is still cold, and it'll only just then start transferring heat around, and you have to do it very specifically, so that way, like this heat will dissipate slowly, and then you can go over here, and then you can go over here, and then you go over here, and then you go over there, and then you go over there, and like that's a different type of sequential, and then like that means if you do it such that like the amount of time that it takes to have that heat dissipate completely throughout all of it, it'll take so long that it's back to being cold again. But once it starts getting towards the middle of it, you do have to let it cool if you want it to be very, very cold. Most of the time I'm able to start around like a 50, let's go with Celsius, like a 10 to maybe 20 degrees Celsius. And I can typically have it come out below 65 C by the end of it without ever needing to put any nitrogen or argon. But if you need it to never, heat up to that amount, then you're going to need to actually, cool it off with standard conduction convection stuff. Right. But this is just sanity check stuff that I did in the past with what it is we had then, what it is we knew about laser wavelengths that we had back then, that we were already doing for 3 up to 5 different wavelengths that they had going on. Then they ended up having eventually knowledge about acoustic wavelength propagation through different materials and how that can influence the likelihood chance of certain types of chemical cleaving and or combo, meaning reactions, right? And along with light and along with electrostatic, electromagnetic, it turned into like, well, why don't we just make a plate and just me? Sounds like it'd be way faster, you know what I mean? So that's where that original concept from the beginning came from, right? But it's like if you want to do this as a basic bare minimum simple, it's really just powder coating with like electroplating, but on a substrate that's not going to have you need to worry about that coming off, right? Because it's getting deposited onto it, but it doesn't have a bond, not realistically, right? And then it does it in such a way that it just sort of like welds it. But instead of using really high temperature lasers and really, really precise and all that, like it's really just pulsing it with the right wavelengths with multiples of them, which is good enough because you don't need it to be below like a millimeter or 0.1 of a millimeter, right? Like a micron is good enough, right? But if you want to get really, really precise, then you need obviously a lot more work being done to that, right? So what I tell most people is start small. You never know how far you might be able to get with those little quartz and silicon dioxide and electroplating styles until you can eventually get to the point where you've got, from the very lasers you started with, a lens system and better programming for your given area that allows for you to get the type of precision that you're looking for that eventually gets you really, really, really stupidly precise 3D printing, right? Especially when it's like, well, we have fiber optics, right? And if we have them dump out and have the right gate system for constructive and destructive interferences, then we have effectively the ability for both substrate, meaning the top and bottom as printers, and the ability to place in acoustic resonances from both the sides and the top with the given type of liquid that's there, but also anything printed from below and above, that allows for you to very quickly produce very large structures in very high precisions that mean you don't have to worry as much about, small defects. Small defects are within like the margin of 3 atoms. And for what it's worth, like that could mean something to someone. It wouldn't mean much to me. So that's my own. Who you want? I'll just slow it down. It'll take another 3 hours, maybe 3 days. It'll be fine. You know what? You want 3 atoms not there? Okay, we gotcha. But yeah, to each their own on a lot of that. You know what I mean? Yeah. So I don't know. For me, it's like 3 atoms isn't going to be a big difference. But if we're talking like 3D printing for chips or organs, possibly, right? That could mean a big difference. You know what I mean? So that could be worth it. So, but otherwise, it's just here's a way to 3D print metal, but it's like there's even like nicer ways to do it where you do both of them. Okay, so remember that spark gap I was talking about? Instead of needing all my laser types, I ended up doing like essentially a vibration method in a vacuum. And so both of the printer heads, well, the substrate was really more like an air hockey table than anything else. And so I'd create little spark gaps there, and then I'd have like essentially a little bit of that acoustic vibration through it, and then I'd basically just make a spark gap right there, and then it would weld it, and then I would just make electromagnetic if it was steel to align it the right way I wanted it to be, and then I'd use light, like a small pulse of electromagnetic, and then a little bit of light that would essentially, as long as it's bright enough and it's pulsed the right way, really precisely align it, and then I'd have a fully formed piece. What that meant was I didn't need to deposit a whole bunch of powder. Like, powder is fairly cheap. I know people saying it's not, but it's like hardened steel powder, okay, right? Just for an FYI, that they'll use in like blacksmithing is pretty darn cheap. Now, the reason why they talk about it being as expensive as they do in their 3D metal printers is because they want it to be less oxidized, okay? Now, when you effectively force a bunch of electricity in a moment with electromagnetic fields and a little bit of electrostatic that runs through it, a little bit of light, it removes that oxygen, and then it congeals down into an atomic, just whatever that is. And that's why the light thing tends to be there, because it's like, well, no, I moved a lot of carbon and I didn't want them to be attached to this oxygen. If it's steel, I don't want that oxygen to take away my carbon content. So it's like I need that light to actually force along with those electromagnetic moments to remain having that carbon content there and have just the oxygen come out as it slowly condenses as it's hot, and then it'll be forced as it condenses again as it cools into no longer having porosity. Now we're talking very small amounts, like less than micrograms of oxygen amount. But it's enough that it means that it can change the material properties. And so if I want to get around that, the only solution is a little bit of light, a little bit of electrostatic, a little electromagnetic with the powder. It could be any goddamn powder practically at that point that is able to be interacted with the right sequence of events. That's all it needs. And then it's done. The reason why they often sell them for the prices they sell them for is because, well, they spend a lot of time researching and developing those sequence of events. Most of the time, they just use really high-powered lasers with very expensive optics that have a lot more going on for all of that. I'm not going to. I'm using multiple lower spec, multiple less accurate parts that will work in conjunction to make more accuracy, more precision, more consistency, be cheaper, last longer, and continuously be able to do that in such a way that you can effectively throw almost any powder in it. One size of a solution is great. When you take multiple solutions together, that means you can use multiple methods and means of control to get multiple greater amounts of accuracy. Once you get to that point, then you end up no longer needing to worry about it. It's the equivalent for me of, well, yes, sure, it takes a lot of people to build a building and have it come out the way you wanted, but it was done faster and it came out the way you wanted and a lot less expense than if you had one or a few people do it and a bunch of really good, very high-tech, expensive machines. Just my 2 cents on it. As I was watching, what was his name? Sunshine. It seems like he's Dutch, but pretty cool. I came up with this myself back in the day. I never had the money to even try it, but it was like electroplating in a very specific area by using like 3D printed areas and then water and electroplating off of that. And it's like, that's a really nice way to do it, truthfully. It's really the fastest, kind of ish, cheapest way. Like the only real way to do it even faster is essentially like powder coating and then zapping with electricity or light and then or both. And that's effectively the fastest you can get it done. That's why when I talked about it a little bit in my comment with the plasma channel, it's like, well, if you use electromagnetic and electrostatic, then you pulse it, meaning you turn on that electricity right when you want it, and then the electromagnetics right when you want it. Then you have the ability to have the metal and the glass both adhere in layers in very specific ways in very specific areas. But it can be in a bath of electroplating, liquid, right? But then that means you can move the electrodes around, and then you can have electromagnetic fields align the metal, but also the glass. And it will adhere slowly over time that way in very specific ways. The only reason why I think people often don't want to do that is because I have to build a machine to make the thing that I'm going to use to do that properly, right? And so I was like, well, behold. Anyways, there you go. I think that hour long will do it. I'm still trying to come up with an acoustic resonance with a static furnace. So, like, let's put it this way: running current, then creating an electromagnetic field, so that way I heat it up, and then I electrically resist it, drop it into a capacitor field that yanks it, and then I create a spark current as I dump more into that, and then dump it onto the substrate doing that. And then I have to have it in a acoustic resonance from the tip area where I have like these little, but very high powerful, very high power uh, speakers, and then same thing on the substrate where it's like I need it to bend a little bit for piezoelectrics to take over. So, sorry, I need it to bend by using piezoelectrics to ultimately have that acoustically match. So it divots and it controls the air environment for it to then deposit. The reason why I talk about it like I need it like that much control is like, what are you firing from forever away? Yes, I'm firing from a very far away distance. Like, in order for fields to be used this way, even with square law, it's a really annoying thing. So I effectively ram it forward, and then I have a big, thing above it that squeezes it as it electrically heats up, and then it dumps into a field, and then it creates a current, and so it goes boom, 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 boom with the acoustic resonance, and so it's far enough away, and then it deposits it as it got shot down, and then it's like, yeah, it's right there, and it's like, yes, except what if, if just hear me out. I decided to do it again. No, please don't. Because like you think I'm like lying when I say this started much higher. Like, I wanted this to fall way further down to get way higher pressures to really basically extrude out a large amount of this powder. So it's like, and it's like, it immediately does a whole big one. And it's like, it's done, right? Yeah, no, that one. We're going to paint again. And behold, the most brute force one there is. I mean it. It was the fastest way I could get it done because I didn't have a way to really like make the equivalent of those big power hammers that like Alex Steele has. I was like, doom, doom, or not. 600 pounds moving like that does not sound like it's going to be very great for precision. If I just need it to go down once and then I do it, then that's way easier. The only reason I'm talking about it is because it's like, well, initially, okay, initially, it's not got much in terms of air, like argon in it, right? As I use argon, and so that comes in hot first and foremost, like 300C. I basically get it up to 300C, and it's like as I bring it up and then I bring it down, which is I think 300 pounds is what I used. It then squeezes it, and it likes to basically take everything to such a way that like the argon goes up, and then now as it's moving fluidically, it has a liquid state, and so now I can pour it through, and then it goes gunk. Now I'm stuck. And so a brief period of time, I'm able to fire it through and then use that as a way to basically paint my 3D print. And so initial, and then initial, and then initial, and then. But it's how I learned off of, I think, either Mark Rober or Veritasium did it for like liquid sand. So it's like if I use liquid sand, well, I mean, what's the difference between liquid sand and metal powder? Nothing. Then why the fuck couldn't I use metal powder? What the fuck is this? I can easily use metal powder. What the fuck is this? That's why the vibrations for the design previous came out. I was like, oh, if I just shake it and then I put a little bit of air in it and I keep it going through, I'm then able to change it with a valve that goes up and down, or spins side to side, and then that'll deposit a certain amount every time, and I can pulse it and then constantly heat it up, have it ready for my print, so I can print really, really precisely all the time. And it's like, metal powder, you would never use metal powder. What? You're just doing to turning it into okay. Oh, behold, your grievances are taken into account, and I did actually make it such that I didn't need to worry about it. Behold, I feel that I am smart enough to think of that face. That kind of thing. Because that's all it would be. It's not even a joke. It literally is. That's it. All you have to do is make sure that it's aerated. In this instance, it's just argon. You use a little bit of argon, then it's like, well, it's able to flow a lot more easily because it's captured in an electrically heated kind of area, which it's like as it's falling, it's of course going to get hot as it goes over those elements. But then it's like, it's not really going to get to the hot that I want it to go to. So it's like, all right, now I've got the furnace. Well, the furnace is going to align the particles. Well, you know what happens if I put current through it? It's like, well, it rips off oxygen. That's great. I don't want oxygen. Well, also, it tends to align everything. Well, that's great, but it also congeals them, right? Yeah, a little bit, but it means it attracts them, right? Yeah, no, that's kind of the problem. So then, what if I pulse it like this? And it's like, it fires then. Yeah, so it's like attractive and then it repulsive. He goes, right, yeah, right. Yeah, and then it goes over to there. And it's like, right. But what if I hit it with lasers to really make sure it does what I want? It doesn't just drop down onto it hot and it doesn't do anything. What if it like really kind of made sure that it stayed together? And then I use like an electromagnetic current, a static kind of thing. So the guy's static was there, and like this is positive, but it's not really. It's more like negative. Well, what if this was positive? And then it's like, well, okay, well then I can use, and that's positive. Okay, so and it's like, and then it does it. Does it just fine. It cools off fast enough. It has no oxygen. The carbon content remains the same. Everything's good. And that's why I designed it the way I did. So now I can print it through a head that never actually gets to a point of heat that wouldn't already be used more or less by most things anyways. I mean, we're talking like, max 500C if like you really needed it to get to that heat. It's really more like about 200, 250, right? But like, I don't need to worry about that because I also have electromagnetic with inside the electro resistive heating, and then I have electromagnetic induction after the nozzle, as it basically takes a big funnel and puts it towards a smaller area. I don't want to get so hot that it sticks to it, right? So that's why the polycrystalline diamond 3D printer heads came into form. If I make it so that way they're like this, then it's like, well, as it gets attracted and I pulse it the right way, like little globs then become a stream. It's like this glob is fast enough to have, globbed and started racing away as this next one's there. And the next one, the next one, the next one, the next one, next one, next one, next one, next one. Now I have a stream of constantly able to be aligned and congealed and welded and fused metal, right? Which is great. That means then it comes out as I want with no porosity, because as I hit it with light, it removes any oxygen and reheats it and keeps it hot or cools it off exactly as I want on its way down. Then it adheres, it gets an electron, and all of a sudden it adheres to the next one, and the next one, next one. Constantly. It's a pulse system. But it's pulsing in a sequence that's so fast that it effectively never has any moment where it didn't ultimately always have exactly what it needed. So, in its chain of events, it was unbroken. In our chain of events, it's a multitude of mini pulses, which is why I talk about shocker for light going forward and backwards and being able to be manipulated to send projections of data forward in time. It can be pulsed, such that because our perception of reality is not, even if it is a constant stream, able to discern whether or not it is being pulsed in. For individuals that were projecting bullshit onto me, thoughts and all that from back when I talked about this in the middle of the 2010s in my parents' Chandler house as a way to 3D print down to the atomic level. And these were my designs I came up with. All right, have a good one. Bye.